line and a plane. Here we'll see the three possibilities between a line and a plane. So here the line lies on the plane. Here the line is parallel to the plane. And here the line intersects the plane. We have seen that the equation of a line is of the form, for example, x minus 1 by 1, y minus 2 by 3, z minus or z plus 3 by 2, and the equation of a plane is 3x plus 2y plus z equal to 4. Now, how do we determine that whether the line lies on the plane, is parallel to the plane, or intersects? For that, we have to compare the direction vector of the line Just to clarify, this is not the direction vector of the plane, this is the direction vector of the normal to the plane. So to compare whether the line is parallel to the plane or not, we have to get the dot product of these two normal vectors, or rather the dot product of these two direction vectors. And we see that this is not equal to 0. So 1 into 3 plus 3 into 2 plus 2 into 1 is not equal to 0. Since it is not equal to 0, the normal vector of the plane is not perpendicular. You can see that normal vector is not perpendicular to the line. Hence, they intersect. So, we need to check if the normal vector of the plane is perpendicular to the line. If yes, they are either parallel, meaning the line and the plane, or the line lies inside the plane. In the example previously, we've seen that it is not perpendicular. So we have the equation of the line as follows, and equation of the plane as follows. So how do we solve this? We solve this by equating the equation of a line to lambda. Now we get x as 1 into lambda plus 1, which is lambda plus 1, y as 3 into lambda plus 2, 3 lambda plus 2, and z as 2 lambda minus 3. We now substitute these values in this equation. So we have 3 into lambda plus 1 plus 2 into 3 lambda plus 2 plus 2 lambda minus 3 is equal to 4. Solving this, we get 6 plus 3, 9 plus 2, 11 lambda plus 4 equals 4, or lambda equals 0. Using this, we've now obtained the coordinate or the position vector of the point intersection between the line and the plane, which is simply substituting lambda in these equations. We get 1, 2 and minus 3. So that's how we obtain the point of intersection between a line and a plane which are not parallel to each other. What happens in a scenario where a plane and a line are parallel to each other? Let's take a simple example. Let's say we have this as the equation of the line, and we have the equation of a plane as x minus y plus z equal to 3. We can see that the direction vector of the normal is 1 minus 1, 1. And the direction vector of the line is 1, 2, 1. The dot product of the direction vector of the normal with the line, with the direction vector of the line, is 0. Hence, the normal is perpendicular to the line, and therefore the line is either parallel to the plane or lies inside of the plane. So how do we check that? By the same process. We assume all of this is equal to a lambda, and we obtain the values for x, y and z in terms of lambda. We substitute this in the equation of the plane. So we get lambda plus 1 minus 2 lambda plus 2 plus lambda minus 3 equal to 0. Here we see an interesting scenario. The lambda vanishes. So we get 0 lambda, 1 minus 2 minus 3, which is minus 4 equal to 0. So we get the equation minus 4 equal to 0. This means there is no solution or no unique solution for lambda. This occurs because there is no point of intersection. They are parallel to each other. If the line lies on the plane, if we have a scenario where the line lies on the plane, we will get an equation of the form, for example, in the previous step, we would get 0 lambda minus 4 equals minus 4. Minus 4 equals minus 4 is true. And this would occur for any value of z. Sorry, any value of lambda, signifying infinite points of intersection. Which occurs when the line is inside of the plane. So, while solving, if we get unique value for lambda, they intersect. This is for while solving for point of intersection of line and plane. If we get a unique value for lambda, they intersect. If we get infinite values, something of an equation like 3 equal to 3, then line lies on the plane. But if we get a wrong equation, example 4 equal to 3, then no solution exists, meaning they are parallel. Hope this is clear. So the procedure involves first equating the line to lambda, getting the values of x, y, and z in terms of lambda, and then substituting in the equation of the plane. Upon solving the equation, if lambda is a unique value, they intersect. If there are infinite values where lambda vanishes, then the line lies on the plane. But if you get a wrong solution, for example 4 equal to 3 and so on, then no solutions exist, meaning it is parallel. The line is parallel to the plane.